So here in lesson 66 we'll be using u-substitution, and this is for integration, and we'll change the variable, and we might look at the proof of the substitution rule. For integration so far we've kind of been doing a guess and check, but we can use this u-substitution idea to eliminate the necessity to do an extra check. So we notice here we have the integral of 40x times x squared minus 5 to the fifth dx. And what we want to do here is we would still want to look at what's the main function going on here. And our main function is this to the fifth power. So what we do is we let u equal what's inside that main function. So we're going to let u equal x squared minus 5. And I'm going to leave a little space here for this first one because we're going to have to do a couple other things here. So we have the integral, and instead of having x squared minus 5 to the fifth, we're just going to have u to the fifth. But this is in terms of dx, and we want to integrate now in terms of u. So what we need to do is we're going to come back to here and we're going to differentiate this. And for the rest of the examples, I'll just do that right away, but we didn't necessarily know we needed that right away. So this is 2x dx. So over here, this is a constant, so I can bring the 40 out here. And then I'm noticing here that I have an x dx. And I want to change that to u. Well, I have this du is 2x dx. So we can write out the work for it here, but what we could do is we could divide both sides by 2, and we will get the fact that x dx, so I was solving for x dx because I have this highlighted part here, x dx, is equal to 1/2 du. And so now what I can do is I can take out this highlighted part, x dx, and I can put in 1/2 du. And I'm going to put them in kind of the correct places here. So moving forward, I can bring this 1/2 out, so I have a 20 times the integral of u to the fifth du. And now I can easily integrate this. So this is 20, and integrating u to the fifth is 1/6 u to the sixth plus c. But my original integration problem here was in terms of x. So now what I do is I plug back in what u is equal to. So we have 20/6, which reduces to 10/3. Reduce that, and it's u to the sixth. Well, instead of doing u, I'm going to put in this x squared minus 5. And then we have plus c. Plus c, not plus 6. And there is the integration of that using this u-substitution idea. So moving on to a few more examples. Here we have another integration. A and b are constants, so we'll remember that as we go throughout this. But as we look at this, our main function here is this square root in the denominator. So we are going to let u equal what's inside that main function. So that's b plus sine of ax. We know from before that we're going to need to differentiate this. So this is du equals, well, differential of a constant is just 0. Differential of sine is cosine of ax times the derivative of what's inside using the chain rule, and then dx because we're differentiating. So I'm going to start plugging in my u-substitution. Again, I can bring this 20 out. And I notice here, well, we have this. I feel like it's going to be a little bit easier to write this as something to the negative 1/2 power. So we have u to the negative 1/2 because we had a square root in the denominator. here we have cosine of ax dx. Well, here's cosine of ax dx. I want to take that out because I'm in terms of u now. Well, I have this a, so I could have divided both sides by a, and I have 1 over a, which I can bring to the outside again since it's a constant, du. So again, I'm plugging in du over a in for cosine of ax dx. So now we can integrate. We have our 20 over a. This is going to be u to the 1/2, and have this 2 out here, plus c, and we'll go ahead and multiply this out and put in or resubstitute in what u is equal to. So we have 40 over a, u to the 1/2, well, we know that's square root, so square root of u, which was b plus sine ax. And there's our answer. So we're able to use this u substitution. Moving right on to the next one. This one actually has something a little bit different in it that we'll get to take a look at. Our main function here is the square root, so we'll let u equal x minus 1. du is simply equal to dx. And so we go to substitute in here. We can bring this 7 to the outside. We are going to change this to the 1/2 power, so we have u to the 1/2. Our substitution here with our differentials, du actually equals dx, so we can take out dx and just put du. But we have a little bit of a problem here because we still have this x. And so this is what's new here. What we can do here is we can add 1 to both sides. And we have what x is equal to, so x will be equal to u plus 1. And so instead of putting x, we can put u plus 1. Sorry, that's crowded in there. So we'll go ahead and distribute that. So we have u times u to the 1/2, where we add the exponent, so u to the 3/2 plus u to the 1/2 du. And now this is just a sum, so this is easy enough to integrate. We have 7 u to the 5/2 with a coefficient of 2/5 plus u to the 3/2 with a coefficient of 2/3, and plus c. And we need to plug u back in, or our value for u, x minus 1, into here. Also, I'm going to go ahead and distribute this 7. So we have 14/5 because of distributing the 7. And this is x minus 1, because u was x minus 1 to the 5/2. Plus, again, distributing the 7 will be 14/3. U is x minus 1, so x minus 1 to the 3/2 plus c. And there's our answer. We could have factored some things out instead of multiplying the 7 in, so that you might have different forms of this answer, but this is definitely a proper form, or proper answer. What we have now is we actually have a definite integral. The last ones were indefinite integrals. So if we were to do this problem, up until now, what we would have done is we just would have done kind of a guess and check here for this. So we have the integral from 0 to 2 of x squared plus 1 cubed times 2x dx. So I'm looking at this, well, I think it's a cubed function, so I'm going to take my guess and say, well, I think that will probably be something like 1/3 x squared plus 1. I'm sorry, not 1/3, 1/4 to the 4th power. I need to check that to make sure it's correct before I go ahead with my definite integral. So that would bring this 4 out front, x squared plus 1 cubed times the derivative of what's inside, and that does give me what we wanted, here. So this is the correct integral. So I'm going to have 1/4. So now I'm going to do the definite integral. I know it's x squared plus 1 to the 4th. And this is going to be evaluated from 0 to 2 because those were, that was the interval there. So we put in 2. So we have a 1/4. Put in 2. Get 2 squared is 4. Plus 1 is 5. 5 to the 4th power is 625. And then we subtract when we put in 0. Well, 0 squared is 0 plus 1 is 1. 1 to the 4th is 1. So 1/4 times 1. Probably don't really need that there. But we have 625/4 minus 1/4 is 624/4. And we divide that and we get 156. So that's what we would have done in the past, finding the definite integral. Well, we can do this u-substitution, and we actually can end up changing these values here since we'll be switching over to u. So we know that a cubed is our main function, so we're going to go ahead and let u equal what's inside that cubed function. We know that du will be 2x dx, and we'll be plugging that in later. And so now we want to integrate, and I'll go ahead and write what we have here. We have u cubed. We see that 2x dx is just equal to du, but this original problem from 0 to 2 is in terms of x. Well, we want this in terms of u now. So what we do is we actually want to figure out, well, what would u equal if we put these values in for x? So I'm going to go ahead and put the 2 in. So u, for that upper bound there, will be 2 squared, x squared plus 1, which gives us 5. So that's our new upper index. And then putting in our lower one here, obviously 0 squared plus 1 is 1. And so our lower will be 1. We won't need to now resubstitute this back in at the end because we changed our variable here. We changed the indexes. So we can integrate here. This is 1/4 u to the 4th, evaluated from 1 to 5. And so we put in 5 and we get 1/4. And this will look familiar, so we have 5 to the 4th, which is 625. Minus when we put in 1, 1 to the 4th is just 1. So 625/4 minus 1/4 is that 624/4 over here, which is 156. So we're able to change our interval here that we're working with when we change our variable. So let's take a look at this one. Our main function looks like it's a sine function, sine of this thing. So we'll, since our main function is sine, we'll let u equal pi x squared, which means du, we know we'll need that, is 2 pi x dx. Start making our substitution here. All we have is this extra x dx, so let me go back. We actually have sine of u, and then this x dx, well, here's the x dx, so we would end up dividing both sides by 2 pi to solve for that x dx. So we have du over 2 pi, which the over 2 pi is a constant, so we can put over 2 pi out here. And we have du over here. Now we have to change our indexes here. So we can plug in 1, our upper one. So this is just pi times 1 squared. So 1 squared is just 1, so our upper one is pi. Our lower, we're going to plug in 0. Well, 0 squared times pi is 0. So we're going to be going from 0 to pi, integrating sine. So we have 1 over 2 pi. Integral of sine is negative cosine. Evaluated from 0 to pi. So we plug in pi. Cosine of pi is negative 1, but it's a negative 1, so we have 1, and then plug in 0, minus 1. So cosine of 0 is 1, but we have a negative 1 here. So this is, sorry about that, minus a negative 1. So we have our integral is the first one minus plugging in 0. When we put in 0, we get negative 1. And so we get 2 over 2 pi, which just equals 1 over pi. And so there's our answer for that one. And the last one here, what's our main function here? Sometimes we can get thrown off by this one, but if we look, we can realize that the e to a power is our main one, because this cosine of 5x, if we did our guessing checking, would come from the chain rule. So let's go ahead and let u equal that exponent up there, so sine of 5x. We know we need to find du. Well, the derivative of sine is cosine of 5x, and then we can use the chain rule, so times 5 dx. We go to do our substitutions, so we know we're doing e to the u power, cosine 5x dx, cosine 5x dx. We have this extra 5 here, so we would go ahead and divide both sides by 5 to make that equal substitution. So we can put in our 1 over 5 here, du, because cosine 5x dx, cosine 5x dx equals that. And now we can go ahead and change the indexes there. So we're going to plug in the top. So this is u equals sine of 5 pi. Well, that's 2 full rotations, then an extra pi, so this is really the same as sine of pi, which is 0. And then plug in 0. So we'll have sine of 5 times 0, which is sine of 0, which is also just 0. So this is an interesting one here. And we learned if we ever go from one number to the same number, it's actually just 0. So our last one turns out nice and easy, since those indexes ended up being the same after we plugged in there. And you could say 1/5 times 0, but it's still 0. So that is using u-substitution for integration.